to discuss the reaction quotient that we just did that little activity for, but we'll actually solve some problems with it. Le Chatelier's principle is probably one of my favorite things in this class. I really like it. You guys will like it. We'll do a little mini lab. You don't have to do a write-up or anything. You're just going to kind of play with it. It's a fun demo observations that you see with colors changing back and forth. And then we're going to discuss how we can manipulate K, Q, and Q, which maybe will take like 2 slides total. So the reaction quotient is what I just described as me saying, question, am I done? Is the reaction done? If it's at equilibrium, then Q will be equal to KEQ. So the AP exam calls it the reaction quotient. You have to write Q for it. You cannot write KEQ until it reaches KEQ. So how can we tell if the system's at equilibrium? The Kc of a certain reaction is 0.042, either given to you or you solved. And then here's the reaction. A chemist tests the system and finds that literally 3 a.m., you get this sample, you run the concentrations, and this is what you calculated. You reported that data. Is the system at equilibrium? If not, in which direction will it proceed? So write out your Kc expression now. Obviously, it's written for you in the next slide, but you should be able to do that on your own, right? So you write out your Kc expression, except you are putting Q in because you're wondering, is this done? It's literally the same thing that you learned in lecture 1, but now you just put a Q because you're questioning whether or not it's done. So you plug in your values. All the concentrations that were just reported to you, you plug in, and you find that Q is 15.6. So most often, your multiple choice questions, it will give you something like this, or for your response, I'm telling you the best thing to do is to write KQ equals products over reactants. You can do this simply because you understand how math works in terms of a numerator and denominator. So if Q, in this case, is greater than KEQ, that means that I want, and just write your numbers down. This is 15.6, but you want, what was the number in the last one? 0.0. Thank you. 0.042. So you want this to go up or down. You want it to go down. So look at this. How do you make this number go down? You have to increase the denominator, right? That makes perfect sense. You want this to go up. So if you want your reactants to go up, then the reaction is going to drive to the left. You say left or right. The reaction drives left, or the reaction will continue to produce reactants. You're going to need to make more reactants. So the reaction will proceed left until the system reaches equilibrium. It is not easy if you just think 15.6 versus 0.042. That's not easy to compare. Don't memorize if Q is greater than KEQ, it goes to the left. Don't memorize that kind of stuff. Just evaluate. This is the expression for this entire section. You should be writing KEQ equals products over reactants constantly because your brain can do this, right? You don't have to memorize anything. You just recognize, okay, this number is too big. I need it to go down, so this denominator has to go up, and the denominator is reactants. Proceed to the left means that the reaction drives left. Like equilibrium is not established, so it's going to have to continue making more reactants. Proceed left. Is left side is the reactant side. So this is just showing you that it's going to continue going to the left until Q is equal to Kc. So the concentration of SO2 will increase and the concentration of Cl2 will increase until the system reaches equilibrium. All right, these are sort of memorized slides, but again, I would not memorize them. Just look at what the data says. So if Q is greater than KEQ, it's going to go to the left because you need to get more reactants. Your denominator has to increase. So just recognize, I would write on my paper, products over reactants, and this has to increase. If the reaction quotient is less than KEQ, again, products over reactants. If it's less, then I need my numerator to get bigger. And so the products will increase. And then if Q is equal to KEQ, then the system is at equilibrium and the reaction's done. Any questions with that? And that's what we were just doing with this activity, is that you kept pulling until you could reach your equilibrium. That's it. And then we're going to solve problems with this one. So let's move on to Le Chatelier's, and then I'll give you some sample problems. Actually, let's pause and go to the back page in your questions, and we'll do a sample problem. Let me pause this. So Le Chatelier's principle is describing what happens to a system when you stress it. So this is like engineering, chemical engineering 101. This is like very basic steps to try and get more of what you want. So in an industry where obviously everything is revolving around money, you're trying to create as much product as you possibly can. But at some point, your system reaches equilibrium and you can't make any more product. But you can stress the system so that you can create more product or whatever it is that you want. And there's 3 stresses. We can stress it by changing the pressure. We can stress it by changing the concentration. And stress it by changing the temperature. This is key. These 2 do not change the KEQ. They cannot change it. In other words, the system will adjust itself so that you always reach that same KEQ. So it'll change the reactants in the product so that it will give you back the same KEQ. Temperature will change the KEQ. And remember I kept saying that over and over. I kept saying this is only the K at this specific temperature. If you change the temperature, you're going to change your K values. So temperature will change your KEQ. So you will see multiple choice questions which will say, which of the following stresses will change the K of the system? And you'll start looking through them and you'll be like, oh, well, pressure will, oh, well, concentration will, but you're forgetting those do not change K, only temperature. The multiple choice questions try to trick you with those. So let's see how they will stress the system. So the first one is pressure. Every single one of the Le Chatelier's principles are based on the fact that if you, and I say buckets, so you may have heard me, someone in a different class talk about buckets. Have you gotten to the buckets yet? You either will get my bucket analogy or you won't. Some people hate when I talk about buckets and they're like, I don't get your buckets. And then like one day you'll be like, oh, I get the buckets. It makes sense. If you are, pretend this is a bucket filled with water and it's only half full and I overfill it and now it's flowing over, I have to get rid of some of it, right? So you always have to go back to the conditions. If it's overfilled, I'm going to go the other way to unfill it. If it's underfilled, I'm going to push to fill it. I want to fill this to the top. If it's not full, the reaction drives to fill it. If it's overfilled, the reaction drives away from it to get rid of some of it. It's a bucket, in a sense. Okay, so if I increase pressure of the reaction, I have molecules floating around, likely in the gas phase. I increase the pressure of the system, and equilibrium is increased. It says pressure is increased at equilibrium is increased. Q changes, and the equilibrium will shift towards the side with fewer moles of gas to reduce that stress. So temporarily, I don't have KEQ. Temporarily, I have a Q where I am not in the range of KEQ. I'm either above it or I'm below it. But the reaction is going to adjust itself to give me back KEQ. So for a moment, you're not at equilibrium, and then the system starts to reestablish itself. So when the system is reestablished, Q will equal KEQ once again. This changes the equilibrium concentrations, but does not change the equilibrium constant. So it's going to adjust itself. So here's how it'll do it. When you increase the pressure, you have a certain number of gas molecules floating around in a certain amount of space with a certain pressure. Pressure is due to the hitting of the walls of the inside of the container. So it's showing me I have 2 moles of NH3, 5 moles of N2, and 7 moles of H2. You can do this on your own, but not right this second. We could set up a KP expression and have NH3 squared, and then the denominator, and we could plug these numbers in, okay? And we could find at this moment what the KQ is, or the Q is. When I increase the pressure, I decrease the volume, and now these particles are going to be exerting more pressure, aren't they? Like too much pressure overall. So the entire system is going to shift away, and it's going to change instead of making 14 gaseous molecules floating around to make 10 gaseous molecules. So what the system will do is it will adjust itself. If you've increased pressure, I need to get rid of pressure. This is my pressure bucket, right? I'm supposed to be at a certain pressure when I'm at KQ. But when I increase the pressure, what happens to the bucket? Does it get full or less full? Overfilling or underfilling? Overfilling, because I've increased the pressure, now I have too much pressure. Get it? It says it's increasing pressure, so I'm overflowing with pressure. So the reaction drives away from pressure, and the reaction is going to drive to fewer moles of gas. Which side has fewer moles of gas? The left side or the right side? Count them. 1 plus 3 is 4 moles of gas on the left, 2 moles of gas on the right. The reaction wants to drive to make fewer moles of gas to reduce that pressure, right? Because I have to empty my bucket. I have too much pressure. So it's going to drive to make fewer moles of gas, and so the reaction will produce more products. That's how you get a more product-favored reaction. Does that make sense? So the opposite would be true if I decrease the pressure of the system. So stress from decreasing. If the pressure on a system at equilibrium is decreased, Q changes, and the equilibrium will shift towards the side with more moles of gas. When equilibrium is reestablished, Q will equal KQ. This does not change the KQ, only the concentrations, only the ratios of those substances. So here I'm starting at a certain pressure. I increase the volume. The volume therefore decreases the pressure. Is my bucket less full or overfilling? I keep saying overfilling, but what's the right grammatical word? I don't know. Overflowing, perhaps. We'll say that. What is it? Less full. So what do I have to do? I have to refill it. So I'm going to drive towards more pressure, and the way to make more pressure is to go to the side with more moles of gas. So the reaction drives to the left to produce more reactants. Following? Okay. Our next stress. Stress is from increasing concentrations. If the concentration of one or more species in an equilibrium system is increased, Q changes. Temporarily, we're not at equilibrium. And the reaction will shift in the direction that will reduce the concentration of that species. When Q is reestablished, it'll equal KQ. This does not change the equilibrium constant. So this is a really simple one that chemists do all the time. And this is just sort of an example of this specific reaction. But basically, before we look at this, this is what you can do. You have in your pot, we'll take this one. I have my Fruit Loops and my Cheerios, right? And it has to be at a specific ratio. I'm supposed to have a certain number of Fruit Loops and a certain number of Cheerios. Well, what chemists will do is they'll say, oh, I want to make more Fruit Loops. So I'm going to take out all of these Fruit Loops, and now the reaction is going to be forced to make more Fruit Loops. Like I literally just take it out of the vessel, the container, and now it has a decreased concentration of Fruit Loops, but I have to reach that certain KEQ, so now the reaction is going to say, oh, I have to make more Fruit Loops because I'm less full of Fruit Loops. Get it? Yeah. If I want to make more Cheerios, I could remove Cheerios, and then the reaction is going to drive to make more Cheerios, right? So if it's overflowing, it drives away. If it's underfilled, it drives towards it. So at this one, it's showing you at equilibrium, I have 1 mole of NH3, 1 mole of N2, and 3 moles of H2. I think this is supposed to say 2 moles of NH3, but it's just giving you 1 here. All right, so then we're moving through this reaction. It's going to show you, let me just hit the slides, is that if you add 5 moles of NH3 here, now my equilibrium is going to be off, right? I'm going to increase the concentration of my products, and its products over reactants. Q is going to be too large, and the reaction is going to have to shift to make more reactants. Get it? I have too many Fruit Loops in a sense. So the reaction has to drive to make more Cheerios to make this ratio be equal. So when I get back to equilibrium, if you guys plug in all these numbers, these two KEQs will be equal. This one temporarily will not. So if you increase the concentration of one substance, it will drive away from it. This bucket is too full when you add NH3. So it drives in the opposite direction to get less NH3. So it'll produce fewer moles of that. Following? Decreasing concentrations. If you remove a substance, this is the one that I was just explaining with Fruit Loops, what is it going to need to do? Make more. right? So it's going to drive towards it. So in this case, your bucket is less full. So you need to fill your bucket by making more of it. So in this example, it's showing you are at equilibrium with a certain number of moles of NH3. But then I remove NH3. So in this example, I have 11 moles of NH3, and I go to 4 moles of NH3. You literally just take it out. You remove it. And so now the reaction's like, hey, I don't have enough in my bucket. I have to refill that bucket. So it's going to drive to produce more NH3. The ratios do change, right? The equilibrium concentrations will change, but the K value will stay the same when it reestablishes equilibrium. And that's how you get more product. As an engineer, you can adjust these different concentrations. All right, dilution. Dilution is sort of the same thing as concentration. If you dilute something, what happens to your concentration? It's less concentrated, right? So say and you guys know this is common sense. You have sodium chloride, and you dump it in, right? But at some point, we'll get to this, the solution becomes saturated, which means that you actually can't dissolve any more sodium chloride, right? The sodium chloride sits at the bottom. This is also true for like sugar. You know that example, but sugar doesn't dissolve, obviously, in the same intermolecular forces that this does, right? Different. This is ion-dipole forces of attraction. So at some point, I get a saturated solution. Well, then I dilute it. So what do I do to dilute it? I just add more water, right? So what happens to this? More of it dissolves. So more of this will go in and produce more ions, and that's exactly what this is saying. You know that already to be true. If you dilute something, it's going to need to drive to make more ions. So if solvent is added to a system at equilibrium, Q changes, because your ions are what you're looking for, and the equilibrium will shift towards the side with more particles to reduce that stress. So look, NaCl, solid, Na plus Cl minus. These are aqueous. So my equilibrium expression here, KEQ, is products Na plus over Cl minus, nothing in the denominator, because you don't put solids, liquids, or gases in the denominator. So then, in order to establish KEQ, if I had concentrations here of like, say, whatever they are, 1 and 2, but then I dilute it, it's going to go down to, say, 0.5 and 1, and then I'm going to need to make more of those ions. So it'll continue to make more ions until the KEQ is reestablished, because there is no denominator in here. So that's what that's saying. So here's an example of HF. I dilute it. It's going to shift to make more H plus ions and F minus ions in order to reestablish equilibrium. Good so far? Going on to the last stress. Temperature is the only stress that will change your KEQ. So you're not going to reestablish equilibrium. It's just going to produce more of either the reactants or more of your products. It will not readjust the ratios of them. Well, it will, but you'll get a different KEQ. It'll just stop. It won't reestablish equilibrium. This is the hardest one. And this one, I think, makes most sense with the buckets. So you either have exothermic or endothermic reactions. Do we agree? If you have an exothermic reaction, you write heat on the product side. So this is really important that you understand where to write the word heat. That will help you solve these problems. So if something is exothermic, you write the word heat on product side. If it's an endothermic reaction, you write the word heat on the reactant side. How do I know reaction's exo or endo? What will the question give me? One of the possibilities. Yeah? It will say delta H is negative. And this one will say delta H is positive. Or it will say the solution or the sample requires heat, or heat is added. It'll give you something so that you know whether or not there's heat on the products of the reactant side. We will definitely try a bunch of these problems because these are the trickiest. So it's showing you this reaction that is exothermic. if I cool this down, are we all looking? If I cool this bucket down, I'm at a certain heat. I have my heat bucket that has to have a certain amount of heat. But I cool it down, so is the bucket less full or over full? Less full, so where is the reaction going to drive? To make more heat. And if the heat is written on the product side, then the reaction drives to produce products, which is why you don't reestablish equilibrium, you just make more products. And then your K value is going to change. If I have heat here, and I add heat, I have my heat bucket, I put in heat. Now is my bucket overflowing or is it less full? It's overflowing, so what's going to happen? It drives away from the heat, which means it's going to produce more reactants until the bucket is back to where it should be in terms of heat. So now this would shift towards the left-hand side and make more reactants. Okay? If you think of buckets, it will help. Hold on 1 second before we try this problem. Yeah, that went too fast. Okay. I just wanted to show you if you have an endothermic reaction. So if heat is written on this side instead, and you cool this down, what will happen? So your bucket on this side, if you cool this down, what's going to happen? It's going to drive back to the left. Do you understand that? I'm just showing you the opposite of this is true. It doesn't matter which side it's on. The heat could be on this side or the heat could be on that side. You are just either driving towards to make more heat if you cool it, or if you've heated it up, you need to drive away from heat to make less heat. Just consider the word heat almost like another reactant or product in that the concentration of it's changing. It's almost like a concentration problem. Okay? All right. So those are your stresses. I think we'll pause, and we'll just go look at some of the Le Chatelier's problems from here, okay? So tomorrow we'll solve some more.
Can you start off with hi, Ryan?
Hi, those of you who are absent.
Ryan.
There might be other people absent today, yep. And then in block 3. All right, so this is a sample problem using Q, which is our reaction quotient, and Le Chatelier's principle. So we have our reaction there. A chemist mixes 80% nitrogen, 20% oxygen by moles in a vacuum and finds that the total pressure is 1 atmosphere at 25 degrees C. Their Kp value is this massively small number, right? So negative 30. Part A, find the initial partial pressure of each gas. Find the equilibrium partial pressures at 25, and then if the temperature is increased to 2,127 degrees Celsius, you get a new Kp, which we know, right? Only temperature can change your Kp. But notice what's wrong with that Kp right away. You cannot eliminate that x value, which is why the quadratic equation would have to be used, or you would end up with a perfect square on the AP exam. You're not going to use the quadratic, though. But you have to pay attention that if your Kp is not less than 10 to the negative 4th, you will have to evaluate something other than just eliminating that small x. We all know what I mean by eliminating the x in the ice chart. Okay. So really when we get down here, I'm just going to show you the answer essentially because we do have to use a quadratic, but that doesn't make any sense. All right, so how do you find the initial partial pressures? Partial pressure, by the way, right, is Dalton's law, which is P total is equal to, and then in this case we have P of N2 and P of O2. That's our initial pressures. And it says that the total pressure is 1 atmosphere when you initially mix these two. So if this is 1 atmosphere, then I have some pressure of nitrogen and some pressure of oxygen. Well, it told me what the percentages are. And we know that the type of particle does not matter when it exerts pressure, right? It just matters how many particles are in there. So if it's 80% by nitrogen and 20% by oxygen, what's the partial pressure of nitrogen and oxygen? 0.8 and 0.2. So this slide is just pointing out to you that you don't have any nitrogen monoxide currently because you didn't start producing it. Just your initial partial pressures of each of these. Agreed? that down? All right, so now it says find the equilibrium partial pressure. So you always write out your Rice chart. You put your reaction at the top. And then we're going to calculate our E line. So just as a reminder, I plus C equals E, and then your E line equals your equilibrium expression. So I always start with my equilibrium expression. So in this case, I have Kp. Why do I have Kp? Because it's a pressure problem. And this is going to be equal to NO squared over N2 times O2. Thank you. All right, so I obviously just started writing this with concentrations, but we need to do parentheses with P and O, parentheses squared, parentheses P and 2 times P O2. So this is the correct expression. All right, so let's just fill in the ice chart. Your initial pressures we already calculated, so you throw those into the ice chart. So 0.8, 0.20. All right, the change lines. Fill those in. You know what they are. Do you? Minus x plus 2x. And then your equilibrium line is 0.8 minus x, 0.2 minus x, and then 2x. So if I'm trying to calculate now my x value, I'm just going to plug it into my expression. So you plug in your values here from that equilibrium line. And NO is your 2x squared. This is 0.80 minus x, 0.20 minus x. Thankfully, our Kp is really small, and we're going to end up eliminating those x values. When you distribute that 2x squared, don't forget to square both the 2 and the x. So this tells us when KEQ is less than 1 times 10 to the negative 4th, you can ignore the x values to avoid using the quadratic equation. So we literally just cross them out. So now this sample problem is 1 times 10 to the negative 30th. This was given to you in the problem. You multiplied 0.8 times 0.2 to get your 0.16. So you multiply these numbers. Your square translated into both pieces. And then you're going to multiply, divide by 4, square root. So make sure that you get this answer from your calculator. If you're not, then you're going to get a calc error. And I'm going to have to take off points. I'll pause while you guys check. So now we're going to evaluate our answer, and the way that you can check is that you put your x values back in, right, to solve. So here's something that's really important. A lot of you will get your x value, and then you'll just stop, and you'll leave that on your paper. But what did the question ask you to do?
Partial pressure.
Of all of them. So don't just write x. What you're going to have to do is write your partial pressure. So that you can do this. You can say, well, since I know that x is eliminated out of these, you could just write out your partial pressures, each of them, by doing P of N2, P of O2, and P of NO. If something is equal to each other, can you guys just look for a second? You could say, like, P of X is equal to P of Y, and then give that number here. You don't have to write it twice. You can kind of put them together and say that. But now these you're going to have different pressures for. So 2x is my NO concentration. Can you guys all look up here? The biggest mistake, if you're going to make a mistake, is that students throw their x value back into this spot to calculate NO, and you get it wrong. Where do you plug in your x value? In your ice chart. That's where you plug it in to find it, not back into the equilibrium expression. The equilibrium expression helped you solve for x. You go always back to your equilibrium line in your ice chart to solve. So your NO pressure is 2 times x. So you get 4.0 times 10 to the negative 16th. And we eliminated our x values out of the bottom. So you're just going to say it's 0.8 and 0.2. Then you can check your work by plugging back in your x value to confirm that you can, in fact, have deleted that, which does still give you the correct answer. Like if you took 0.8 and subtracted in your calculator 2 times 10 to the negative 16th, you're still going to get 0.8. So you can check your work and realize that that was okay, that you eliminated that. The other way to do this is to plug all these numbers back into your equilibrium expression. And if you get the Kp value here, then you also know that you did this correctly. So it's just confirming that you can eliminate x if you go back and check it both ways. All right, the next problem, though, asks you to find the new equilibrium concentrations given the new Kp. We are not doing this. Got it? So you're still going to do the same exact chart here, except the point of this is that you cannot eliminate Kp, the x value. So since your Kp is so large, in a sense, it's not less than 10 to the negative 4th, you have to include it in your expression. And then if you're going to do that, then you're going to have to solve using the quadratic. I'm telling you, on the AP exam, you don't have to use a quadratic, but what they will do is make it a perfect square of some sort that you will be able to just get rid of everything. Okay? Like maybe it'll be, here I'm going to try another terrible example and probably fail, but maybe it's like 4x squared divided by like 0.8 times 0.8. Like maybe both of those pressures are 0.8 and 0.8 minus x or whatever it is. And then you would square root the whole thing to get rid of it all. Get it? If I square rooted this, I would get 2x over 0.8, I hope. Okay? So let's just get rid of all of that. All right, so last two pieces here, I think there's 2 more slides left, is how do you manipulate K, Q, and Q? So 2 ways, the reciprocal rule and the multiple equilibria rule, which just means that sometimes you can take your reaction, sort of like a Hess's law, and you can manipulate it. So you could flip the reaction, and then there's a rule for what you do when you flip it. And then when you multiply them together, like I have reaction 1 and reaction 2 to give me reaction 3, just like Hess's law. Except in Hess's law, we add them up. Here you multiply them. When you flip something in Hess's law, we multiply by -1. Here you use the reciprocal. So just 2 quick slides here. The reciprocal rule says when a reaction is reversed, the new KEQ or Q value is the inverse of the old KEQ value. So you literally do 1 over that K value. This is the most important thing. 1 over it. So it's showing you that I have 2A plus B yields 6D. And this is how I would write it. But if I reverse my reaction, then I have to reverse my K value. So I have to divide 1 divided by that K value. You guys remember that problem that I gave you yesterday where not anyone really got it right and I had to show you part C? Remember in that problem we started with products? Remember that problem? And you had to go backwards and figure out what you made. If you ever wanted to, you could always use your original KC values and just do it the way that it gives you. But if you start with products, you could reverse your reaction and then use the reciprocal rule on your K and then solve it that way if you wanted to make it a forward reaction. Yep?
I'm saying for that, wouldn't you also have to square root the K and Q?
Yes, on both sides. If you had a K value or back to this one, you would square root both of them. Yes. All right, so just 1 over that K value would give you the reciprocal. Good? So if you flip it, it's 1 over. In Hess's law, we multiply by -1. Here, it's 1 over that. This is note card worthy. This is the kind of stuff come May that you may forget. This should probably be reminded to you. All right, multiple equilibria rule. It says when 2 or more reactions are combined, the new KEQ or Q is the product of the KEQ or the values from the individual. Product is most important here. You multiply them. In Hess's law, we added them up. We summed our H's. But here, when you combine these, you can still, just like Hess's law, you cancel out your A's, and then you end up with 3B, and then 2, 1, 2 here, 6D, and then 1F. So if I'm going to write the equilibrium expression of this one, that's what it's showing you here. This is this piece. These are these pieces. You can see that if I multiply them, these will cancel out from each other. So all I did is products over reactants, and then here I did products over reactants, and my A squared value cancels out. So this does in fact give me the same K value or K expression as the final product. So all you do is you multiply them to give you the new one. That's it. All right.